Okay, so this video is going to be all about how to prepare for exam 2, what all the resources are, and the topics that are going to be on the exam. So let's just go through this real quickly. So what I'm doing is I'm putting all of the videos that I've made in one playlist. So everything that's going to be for exam 2 is going to be in that playlist, and so that includes solutions to all the old homework, the derivation of the acceleration and velocity vectors in polar coordinates, and the step-by-step guide showing how to use Newton's second law for problem solving. So the problem solving strategy, remember I did that assignment that was a whole bunch of really short videos. That's in there as well. So my biggest suggestion for preparing for the exam is work as many problems as you possibly can. The more problems you can work, the better. And I'm making a lot of problems available to you so that you literally have more problems that you could work on than you have time to actually do. So that includes WebAssign, both the new practice and the old homework. So what I did for the new practice, and like I said, there are way more problems than you can possibly work. I basically dumped all of the questions from all of the chapters on the exam into assignments that you guys can work on. These are just practice. It's not extra credit. It's not for a grade. I'm just giving you as many problems for whatever style you like to work problems as possible. Okay. So there's also old exam questions that I posted. So honestly, I think the WebAssign is good to a point. This is better. These are much better problems to prepare you for the exam than the WebAssign problems are. Let me just show you what this looks like really quickly. So down here is, this is actually my exam 2, but basically these assignments are the same. It's just, these are the ones from the exam that I took. And then there's also the ones that, it's just a big long list of problems like this that I got from the professor that I used to teach with, who wrote these style of problems. So let me show you that really quickly. So there's a whole bunch of them. Like, there are a lot of these problems for you to work on. So you do all of these, you're going to be in pretty good shape. And at the bottom, there's some circular motion questions. These are a little bit different than the kinds of circular motion questions that we would ask you, but not completely. Because when they did this where I used to teach, this was later in the semester. But doing the circular motion problems are good practice, and doing all of these forces and work energy and conservation of energy questions that are here are really, really going to help you. There's also the practice exam on the meta course as well. So there's, like I said, there are a lot of things for you guys to practice. Okay. Now, what I will say is, per my old exams, the team assignments, and the old exam questions that I posted, these are going to be very similar to the type of question that I'm going to ask. Now, the one that is on our exam is not as open-ended. There are numbers, and there are, and it's stratified. So it's not like find the velocity, just go. Okay, it's built up to what it is that you need to do. So the reason why I like to give you guys assignments coming from me, part of the reason is that you get a sense for how I write questions. And if you've been doing the team's assignments, you'll basically be able to look at the exam and you'll know which question I wrote. You're going to understand my style and my approach to writing questions. And ultimately, that's going to make it a lot easier for you, because you've heard it from the horse's mouth. You've seen the way that I write questions. You're beginning to kind of think the way that I think in terms of the way I approach question writing and the way I approach problem solving. So I mean, I can't tell you which question I wrote, but I will say that if you've done my homework, my assignments, and even if you haven't, if you start doing them now and you look at the old exam 2, you look at the team's assignments, my problem is going to be very much in line with the way that I ask questions. Okay, so topics for the exam: Newton's second and third law for translation. This means free body diagrams determine acceleration for a single mass and collection of masses. So I had a whole bunch of the problems that I did that were like this. You have the solutions to those posted in your notebooks, as well as the videos where I went through and solved those. So don't just watch the videos. You need to make sure that you're solving the problems on your own. Okay, so Newton's second law for rotation, centripetal acceleration, both for linear and angular velocity. So that's the v squared over r and the r omega squared. And the special acceleration that you have for circular motion being the centripetal acceleration. So you know that when you're applying Newton's second law for rotation. You can evaluate what the acceleration is in the radial direction by saying it's the centripetal acceleration, or well, it's the negative centripetal acceleration for the way that things are defined, but you guys know what I'm talking about. The work energy theorem. So be comfortable with the integral definition. Have how to take a dot product. What is a little slice of path? How do I find endpoints and limits of integration? And when is work negative? These are all important considerations, because you're not guaranteed to have something with a constant force for all of the questions for the work energy theorem. So you're going to have to know, for instance, how do you derive the equation for the potential energy of a spring, right? And basically, all like I've done a whole bunch of these kinds of problems for constant forces, but it's the same process when you're doing it for non-constant forces. It's just you're not integrating something that's constant. Okay, so keep that in mind. Conservation of energy and energy bar charts. This is a little bit harder for me to go into as much detail for what to do. So the work energy theorem, like it's a nice box that you can put all the things in. Conservation of energy and energy bar charts are harder to define exactly what it is that you need to do. But I think the best thing I can say is just practice as many problems as you possibly can. Know how to define potential energy for springs and gravity, how to incorporate friction into bar charts, and defining coordinate systems. And when I'm talking about gravitational potential energy, does this have a potential energy of 0? Does it have a potential energy of whatever the height it is above my desk? It really matters how I'm defining 0. And so you need to be very careful with energy bar charts and conservation of energy when it comes to gravitational potential energy, because it really matters how you're defining your coordinate system and where you're measuring your gravitational potential energy relative to. We're going to be practicing that a bit more in class tomorrow. Okay, the last thing, and I'm not even going to talk about this in class, or I guess I'm going to have to, but power is also something that's going to be on there, but it's such a minor topic that it's basically, can you calculate work and then divide it by time? Like, how long does it take to do that work? What is the duration of the work? Take that work, divide it by the time. That's what power is, and that's literally everything there is to say about power. I'll probably repeat it again because not everybody's going to see this video, but no power. That's a given. That'll be on the exam, and per all of the other topics and how much more detail we go into them, I would not spend as much time on this. I would focus most of your time on these 4 topics here. Okay, so that's going to be it for this video. I'll see you guys when I see you, and good luck studying.